Welcome back, everybody, to another day in Algebra 1. Today we are talking more about factoring, and more specifically, factoring completely. So, a couple reminders. Again, homework collection 14s this week. Make sure we're chipping away at that homework daily. The homework collection is only through tonight's homework, so you should have it ready to go on Thursday when it is actually opened up. So don't procrastinate, get that done. And we're down to like 20 some days of school left. So if you're missing homework, test quizzes, get that stuff done, get it turned in. You can still get credit for all that stuff. Again, end of the school year is coming quick. So today, again, talking about factoring completely. Going to pull the answers up for 813's homework from last night very quickly, and then we'll jump on into some toolkit notes and talk about factoring a little bit more. So here we go. Homework answers. Again, pause the video, check the filled-in notes if you want to see them in a little bit more detail. Otherwise, moving on. So we're going to start with some toolkit stuff. So follow along here. Make sure we get this out, get this filled out. So a quadratic equation is an equation written in the form of, let me get my notes in front of me here, ax squared plus bx plus c, where a, b, and c are all constants, kind of like we can see here, like 1 in front of x squared, 5 in front of x, and that's 6 at the end. When we have the factored form, that is when a quadratic is written as a product. So just like this right here, that's our factored form. We have two sets of parentheses, potentially more stuff multiplied next to each other. So again, it's not the ax squared plus bx plus c. It's the whatever set of parentheses double distributes together to make that quadratic equation. So if we want to factor a quadratic equation, first thing we do is fill in the parts of the generic rectangle that we know for sure. And that is the bottom left and the top right. So we know bottom left, right off the bat, and top right. So the bottom left is always the x squared term. So in this case, it is 2x squared goes right here. The top right is always our number at the end, which is 6 in this case. So those go in those two respective spots. So now we're going to use the pattern that we discovered from our generic rectangle to say that the diagonals multiply to the same product. So diagonals multiply to the same product. So again, since the diagonals of the generic rectangle must multiply to the same thing, we know that the missing parts of the generic rectangle must multiply, in this case, to 12x squared, and then add to 7x, which is the middle term of that quadratic equation. So the middle term tells us what those two missing boxes add up to. Again, they multiply to the same thing as 2x squared times 6, which in this case is 12x squared. So now we got to solve our diamond problem. And again, how we do that is we put what the two things multiply to on the top, which in this case is 12x squared. 7x is what they add to. That goes on the bottom. And these two boxes, these two remaining boxes here, this guy and this guy right here, represent the two missing boxes in our generic rectangle. So now we just got to figure out what multiples of 12 basically add up to 7. So if you ever get stuck with this, what I would recommend doing, make a list of all the multiples of 12 that you can think of. So for example, we've got 1 and 12, we've got 2 and 6, we've got 3 and 4, and I think that's it. So now we got to figure out which ones add up to 7, and that's going to be 3 and 4. So here we got to put 3x and 4x. And now we can plug those numbers back into our generic rectangle. Doesn't matter which spot we put them in. I'm going to put 3x here. I'm going to put 4x here. And I'm going to continue down the page. I'm going to copy that into this bottom generic rectangle. It's the exact same thing. So we got 3x. We got 2x squared. We got 4x. And 6. Perfect. So now we can use the left and the right-hand parts of the diamond to complete our rectangle. And now we want to figure out what our side lengths are that basically multiply together to find the areas of these smaller respective boxes. So for example, what multiplies together to get x or 2x squared? Let's start with that one. So in order to get 2x squared, we have to multiply 2x times x. Because again, 2 is a prime number. The only two numbers that multiply together to get 2 are 1 and 2. So we know that there has to be either an x or a 2x in either this spot or this spot. So I'm going to say that we need to put the 2x right here. And the reason for that is that if we put 2x down here, if we try to multiply something by 2x or 2x by something to get to 3x, I don't think there's a whole number that can do that because 2 is not a multiple of 3. So we cannot put 2x right here. Instead, that has to be that single x, because now 2x times x is 2x squared. Now if we want to think about what do we have to multiply x by to make it 3x, this is going to be 3. And again, what do we have to multiply 2x by to make it 4x? This is going to be 2. Just to double check ourselves, 3 times 2 tells us that we get 6. So this is indeed the factored form of this quadratic equation. So we, again, have our original quadratic, 2x squared plus 7x plus 6 is equal to 2x plus 3 times x plus 2. There we go. So there's our toolkit notes for today. We're going to add some more stuff to this a little bit later in the week. But let's jump into the lesson for today. And today we're doing 814, again, factoring completely. So 35 is all completely review. It's the exact same process that I just talked us through, factoring quadratics. Again, knowing that we have, again, the squared term goes in the bottom left, the number goes in the top right. So what I'm going to let you do is do A, B, and C as a little review and some practice for you. I'll put the solutions in the filled in notes, so go ahead and check that when you finish watching the video. Remember, whenever we see something like in part B, we want to make it look like ax squared plus bx plus c, so that way we know what or where the different things from our patterns go, like we talked about in our toolkit. So whenever we see something where we're missing a part, we should always plug in a 0 for that missing variable. So this one really should look like 81m squared plus 0m minus 1 before we try to solve. So a little hint on that one. Try A, B, and C on your own. We're going to walk through D together because that's going to set us up nicely for the rest of the way here. So again, let's work through this together. Plug in the stuff that we know for sure, which is the n squared term and the 6. We can plug those into our rectangle. So this is 3n squared. This is 6. So we know the product of these two things goes on the top part of our diamond problem. So this is going to be 18 and n squared. The bottom part is the middle term in our quadratic equation, where these two empty boxes add up to be 9n. So now we need to think about what multiples of 18 add up to be 9. So let's make a list of all the variable or the multiples of 18. So I'm thinking there's like 1 and 18, there's 2 and 9, and I think 3 and 6 are the ones that I can think of off the top of my head. And I think the ones that are going to add to 9 are obviously going to be 6 and 3. So we need to put 3n here. Let's put 6n here. And remember that these two blue numbers are the ones that go also on our generic rectangle. So now we've got 3n, and then we've got 6n right here. And now we're ready to factor, because as soon as we get this thing all filled out, then we can start factoring. So I'm going to start with the 3n squared in the bottom. So we know that 3 is a prime number. So the only two things that multiply to get 3 are 1 and 3. So let's see here. We need to know we have to put either 3 or 1 here and 3 or 1 here. So let's see if we can make this work by putting 3n on the bottom. So if we take 3n down here, what do we have to? We don't have to multiply this side by just a regular old n, because 3n times n is going to be 3n squared. Now 3n times 1 is going to get us to 3n in this box, so we got to put a 1 right here. And then if we take n, multiply by something to get 6n, that is going to be multiplied by 6. So we have 1 times 6 now, so that top right-hand box is all taken care of as well. So our final factored form is going to be 3n plus 6 times n plus 1. So that is one way that we can factor this. I think, though, that we can maybe do it one more way as well. So I'm going to put a second set of numbers in purple right next to these because we, I think, can factor this one more way. So that green solution is one set of solutions. What if we put this 3n over here instead and put this as n? Can we still factor that, but we flip those two spots around? So 3n times n is going to be 3n squared. Now if we take 3n, what do we have to multiply 3n by to get to 6n? That is going to be 2, so we put 2 here, and then we take n, making it 3n here, so we're going to make this a 3. So there are potentially two solutions for this one. We get 3n plus 3, and then n plus 2. So we do get two solutions for this. Either one of those would be acceptable. But what I want to understand is why in the world are we getting two solutions when most of the ones that we've seen so far have only had one? So that's what we're going to dig into in just a little bit here. Factoring completely. We only want one solution. We don't want two because two is kind of confusing. So let's just get that thing down to one solution. So again, like we just talked about, this is the problem we just went through. Is there more than one factored form of 3n squared plus 9n plus 6? And as we saw, absolutely yes. Yes. So again, we had those two factored forms. Sorry, as I'm sliding out of the way to turn my lights back on. But we did have those more than one way to factor that one with those two solutions of 3n, put those back on here, 3n plus 3 times n plus 2. And then we also had 3n plus 6 times n plus 1. Those both got us exactly the same thing. So why is that the case? So if we look at that equation again, that highlighted equation, why does that only have one? Why does it have more than one possible answer? So what I want us to do is look at this equation again. Is there anything extra that all of these numbers might have in common that might be contributing to the fact that we have more than one solution? So as I look at these three numbers, so 3, 9, and 6, I think they're all multiples of 3. They are all multiples of 3. So if maybe we're able to factor a 3 out in addition, or if we're able to factor a 3 out before we actually factor, I think we could probably get down to one solution. So what this is telling me is that if all three terms A, B, and C in ax squared plus bx plus c share a common factor. Oops, let's not shake. Let's fix that. Share a common factor. In our case, in our example here, that common factor was 3. We will have more than one. Will have more than one solution. So let's move on to part C. It's at the top of the next page for y'all. Without factoring, predict which quadratic expressions below may have more than one factored form. And again, going off that thing we just talked about, if they have a common factor, they will probably have more than one solution or more than one factored form. So part 1, we've got 12, 10, and 2, or negative 10 and 2. All of those are divisible by 2, so they share a common factor. That one's probably going to have more than one factorable form. 5 to negative 23 and negative 10, that one does not have a common factor, so those are probably not going to have more than one factorable form. 10, 25, and negative 15, all divisible by 5. So again, that one probably going to have more than one factorable form. And last but not least, number 4, we got 3, 7, and negative 6. Again, they are none of those share a common factor other than 1. So again, probably we'll have one solution for that one, if one at all. So there we go. There we go. So there's 36. Let's go to 37. We're going to talk about factoring completely. So with that, along that same line, if we want to factor something so we only get one factorable form, if all three terms, those a, b, and c terms in ax squared plus bx plus c have a common factor, we want to factor that out before we actually try to factor and get our quadratic expression into our factored form. So basically what I mean by that is, let's take a look at 10x squared plus 25x minus 15. So, sorry about that, folks. So let's try to get to, or what is the common factor between these two numbers? So 10, 25, and negative 15, they are all divisible by 3. Or not 3, they're divisible by 5, not 3. Divisible by 5. So if we divide every single term by 5, basically we're taking the 5s out of each term, we would be left with 5 times 2x squared plus 5x minus 3. So we factored that 5 out, and now what we can do is we can use our pattern from before to factor just what's left after we factor out the 5. So now we can follow our pattern that we put on our toolkit just a little bit ago, where we have 2x squared here. This is negative 3. So the two empty boxes add to 5x, the middle term of the stuff inside our parentheses. And those two missing terms multiply to add to, or not multiply, they multiply to negative 6x squared. So now let's figure out multiples of 6 that might add up to positive 5. Multiples of negative 6. We got 1 and 6, and then 2 and 3. Those are the only two sets of multiples for 6. And again, if we've got negative 6, we have to have one positive and one negative for our two side pieces here. So let's say that we have maybe 6x and x, or 1x. Perfect. We need a positive 5. So 6x times 1x is going to be 6x squared. So we still got to make one negative. We need a positive 5. So I'm going to make the negative 1. I'm going to make the 1 negative, I should say, because now we have 6 minus 1, which gets us to 5. 6 times negative 1 is negative 6. We are all good to go. Let's plug those in and factor. So now we got negative, or 6x minus 1x. Again, we've got 2x squared at the bottom left. So I'm going to put my 2x down here because 2 is not a multiple of negative 1. We have an x right here. 2x times 3 is going to get us to 6x. X times negative 1 is going to get us to minus 1x. And then 3 times negative 1 is indeed negative 3. So this x plus 3 times 2x minus 1, so x plus 3 times 2x minus 1, is the factored form of what was inside that there's the highlighted chunk right there. So our final answer is we're just basically taking these two sets of parentheses, substituting them in for that highlighted chunk. Our final answer is going to be 5 times 2x minus 1 times x plus 3. Our one factorable form, factored completely because we factored our common factor out for both of those. All right, so I'm going to do two more with us very quickly. We're going to go to 38 at the bottom part of the page. So we've got B and D are the ones I'm going to run through. A and C are yours to do on your own. So here we go. Let's jump into part B. So again, we have a common factor. If we want to figure that one out first. If we ever see something like this, is there a common factor? What might it be? What can we factor out? So we have 3, we've got negative 6, we've got negative 45, we've got x to the third, x to the second, and x. So every term has an x, so we can factor an x out for sure. And every term is also divisible by 3. So I'm going to factor out 3x from this equation. So that we're going to factor out 3x. So we are left with x squared minus 2x. And then we are left with minus 9, I believe. No, minus 15. Minus 15. Wow, minus 15. There we go. So minus 15. Now we are going to factor just what's on the inside of these parentheses right here. So the 3x is good to go on the outside. We want to factor x squared minus 2x minus 15. So x squared goes here, negative 15 goes here, negative 2x x goes right there. Now we want to figure out what goes on the top part, so we take x squared multiplied by negative 15. The top here is negative 15x squared. Perfect. Now we need to think of multiples of 15 that might add to negative 2. Negative 2. So again, multiples of 15, 1 and 15, 5 and 3. I think that's the ticket that we need right there. So I'm going to make this one negative 5x. I'm going to make this one 3x, because when we add 3 to negative 5, we get negative 2. Negative 5 times 3 gets us negative 15. Our x is also multiplied to get x squared. We are in business. I'm going to move these over. Negative 5x. We have 3x here. There's only one possible solution for x times x. So we have to put an x here, put an x here. X times negative 5 makes this negative 5x. So this is negative 5. And this has to be 3, which will end up being our final, or give us our final solution here when we plug everything back in, of 3x times x minus 5 times x plus 3. And there is our completely factored version of part B. Wonderful. So let's move on to part D. D, our greatest common factor in this case is not a number, but instead it's a y, because every term has one y. So to factor this one, what we want to do is, again, factor the y's out. So when we do that, we are left with y times x squared minus 3x minus 10. And now what we're trying to do is just factor the remaining stuff inside of those parentheses. And again, now we're just following our pattern just like before. So we have x squared, we've got negative 10. So in our diamond pattern, these things add up, to the empty boxes add up to negative 3x. On the top, they multiply to negative 10x squared. So multiples of negative 10 that would add to negative 3. I think there's only two options for us, either 1 and 10 or 2 and 5. So I'm going to use 5x and 2x, because if we make 5 negative, if we add 2 to it, we get negative 3. If we multiply negative 5 and 2, we get negative 10. So we get negative 5x and 2x for our two missing squares. And now we can factor. We got x times x, so this is x, this is x, this has got to be negative 5, this has got to be 2. So our final answer is going to be y times x minus 5 times x plus 2. And that is our final answer. So finish those other two on your own. Some good practice. So find the common factor, factor it out. For part C, again, add the missing term in the middle before you start trying to factor this, to make sure we don't put stuff in the wrong place. Other than that, the homework for this evening, everybody, is 8.1.4. Bring some questions to class on Wednesday or Thursday when you have them. Otherwise, check It's Learning on Wednesday, because we also have a quiz. Let us know if you have any questions. Otherwise, have a great day, everybody, and we will see you on Thursday.